ズム小型月着陸実証機スリム打ち上げをライブ中継でお届けしてまいります。このライブ中継は日本語のほか英語の同時通訳で世界中にお届けしています。世界中の皆様おはようございます。こんにちは、そしてこんばんは。どうぞ最後までお付き合いください。私はこの番組の進行を担当します JAXA 宇宙科学研究所の鳥海慎と申します。専門は太陽物理学です。普段は JAXA の日の出衛星を使った研究やソーラーシー衛星の検討開発を行っています。今日は待ちに待ったクリズムスリムの打ち上げ、これまで延期しておりましたが今日こそはということで私も楽しみにしております。最後までよろしくお願いいたします。そしてこの相模原の特設スタジオには、今回の打ち上げを皆さんに分かりやすくお伝えするためにそれぞれのプロジェクトの皆さんにお越しいただきました。いずれも各分野の世界的研究者の皆さんです。ご紹介してまいります。まず東京理科大学理学部第1部クリズムの、プロジェクトサイエンティストであります松下京子さんです。松下さん、よろしくお願いいたします。
はい、よろしくお願いします。松下です。クリズムのプロジェクトサイエンティストとしてクリズムの科学観測計画のいろんなお世話をしています。普段は銀河や銀河団の観測を行っていまして、データが降りてくるのをすごく楽しみにしています。前回は残念なことに天候が不順だったんですけれども、今日はなんとか天候が持ってほしいなと思っています。
はい、ありがとうございます。よろしくお願いいたします。続きまして愛媛大学大学院理工学研究科クリズム科学運用チーム志達めぐみさんです。志達さん、よろしくお願いいたします。
よろしくお願いいたします。愛媛大の志達です。私はクリズムの科学運用チームというところで衛星から降りてきたデータをユーザーの方が使いやすいようにですね、整理して加工する地上データ処理システムの開発や試験などに携わってきました。普段はブラックホールの研究をしていますので、クリズムを使ってどんな新しいことがブラックホールに関して分かるのかと、そういった話もできればと思っています。よろしくお願いいたします。
はい、よろしくお願いします。ありがとうございます。続いてスリム側のお二人です。まず JAXA 宇宙科学研究所スリムプロジェクトメンバー森修さんです。森先生、よろしくお願いいたします。
おはようございます。よろしくお願いします。私はスリムの推進系の開発に携わっています。それと将来の月探査計画を進めているメンバーでもあります。特に将来計画検討すればするほどですね、このスリムの技術というのが欠かせないものだというふうに感じています。ですので今日こそはですねうまく打ち上がっていいスタートが切りたいと思っています。どうぞよろしくお願いします。
はい、よろしくお願いします。ありがとうございます。続いて会津大学コンピューター理工学科スリムペイロードマネージャーの大竹真紀子さんです。大竹さん、よろしくお願いいたします。
よろしくお願いします。会津大学の大竹です。ペイロードマネージャーということで、スリムの観測によって得られる成果を最大にするためのお手伝いをさせていただいています。あとは観測機器の開発のお手伝いもさせていただいています。普段は月面の観測データから月の地質解析を行っています。ですので今回のスリムの打ち上げについては私も一研究者としてとてもワクワクしています。よろしくお願いします。
はい、よろしくお願いします。ありがとうございます。皆さん、4名の皆さんには後ほど詳しくお話を伺います。どうぞ最後までよろしくお願いいたします。ではここで今回の計画についてご紹介していきたいと思います。まずは現地の様子を確認しておきましょう。種子島宇宙センターの様子ですが、昨夜すでに機体を車上に移す作業も無事に終わっております。現在の様子ご覧いただいている通り穏やかな天候の様子です。はい、続いて本日の飛行計画と使用シーケンスをご紹介します。H2A47 号機は地球の周りを周回するクリズム衛星と月へ向かうスリムの合計2機を搭載しています。したがって今回の打ち上げの特徴というのは2段階に分かれた飛行計画となっているところと言えます。打ち上げはこの後日本時間午前8時42分11秒を予定しております。打ち上げからおよそ1分30秒後に固体ロケットブースターが燃焼終了しまして、その15秒後に分離されます。打ち上げ4分10秒でまず上部衛星フェアリング、これはクリズム衛星をカバーしているフェアリングですが、これを分離いたします。さらに6分30秒過ぎたあたりで第1弾を分離、第2弾エンジンに点火いたします。 打ち上げから13分経ちますと、燃焼している第2段エンジンを一旦止めまして、打ち上げ14分21秒後、日本時間の午前8時56分32秒にクリズム衛星の分離を予定しています。さらに打ち上げ17分が経ちますと、スリムを覆っている下部衛星フェアリングを分離しまして、しばらくそのまま飛行を継続します。この間はエンジン点火しない完成飛行となります。打ち上げ44分が経ってから第2段エンジンに再度点火しまして、約2分間燃焼を行います。打ち上げ47分39秒後、日本時間の午前9時29分50秒にスリムを分離する予定といった飛行計画になっています。分離時刻はよくご質問いただいているところなんですけれども、クリズムが打ち上げてから14分21秒後、午前8時56分32秒、それからスリムの分離が47分39秒後ですので、日本時間の9時29分50秒となっております。はい、でここでですね、森先生にお伺いしたいと思います。当初8月26日の打ち上げ予定ということになっておりまして、そこから延期して今日12日ほど経っているわけですね。はい、で当初8月26日の時は打ち上げの時刻が午前9時34分で、本日の打ち上げ予定時刻は8時42分ということで、打ち上げの時間がだいたい45分ほど早くなっているわけですね。はい、これはどういった理由からなんでしょうか。
これはですね、スリムの軌道に関係しています。ちょっと簡単に紹介しますと、こちらスリムの模型なんですけども、こちら地球だと思ってください。今日ロケットで打ち上げられると、スリムはこの地球の周りを回る、地球周回軌道というところに投入されます。で、この適切なタイミングでこの地球を出発して月に向かっていくわけなんですけど、この打ち上げ日にかかわらず、この地球を出発するタイミングは同じにしたいというふうに考えています。そうすると、この今日投入される周回軌道っていうのは、日にちにかかわらず、打ち上げ日にかかわらず、同じでなければならないという、そういう縛りが発生します。で一方ですね、地球は太陽の周りを1年で一周しますので、1日1度ずつ動いていってしまいます。ですので同じ時間に打ち上げると軌道が、スリムが入る軌道がずれてしまうということになります。で、同じ軌道に入れるためには4分間ですね、早く打ち上げないとならないということで、1日4分早くするということで、今回12日間遅くなったので、40数分間早く打ち上げることで、同じような軌道に入れることができるという、そういう仕掛けになっています。
なるほど、ありがとうございます。スリムが月に向かうための軌道っていうのは決まっていて、はい、でその軌道に種子島から打ち上げるタイミングっていうのは、その軌道にぴったり合うようなタイミングで打ち上げたいんだけれども、はい、地球自体はどんどん動いていってしまっているから、はい、だからその種子島からの打ち上げがその軌道にぴったり当てはまる時間っていうのが少しずつ毎日ずれていく。でその結果、12日間でだいたい45分ぐらいずれていったっていうことなんですね。
はい、そうなります。
なるほど、ありがとうございます。今回延期したからといって、例えばその機体であるとか衛星の状態には、特に問題はないと考えてよろしいでしょうか。
はい、もちろん問題ありません。
はい、ありがとうございます。前回中止したとはいえ、前回はその上空の風が強すぎた、打ち上げ条件を満たさなかったということで、機体自体には問題なかったというわけなんですよね。なのでこの延期というのは打ち上げに万全を期するためであると、延期をしたけれども機体と衛星の状態は今も良好であるので、今日の打ち上げを判断したということになっているわけですね。はい、ありがとうございます。ここで今回打ち上げられるクリズム衛星についてご紹介していきたいと思うのですが、初めにですね、クリズムのプロジェクトマネージャーからのメッセージが届いておりますので、プロジェクトの紹介と合わせてご覧ください。
JAXA 宇宙科学研究所クリズムプロジェクトマネージャーの前島です。我々が開発したクリズム衛星がいよいよ打ち上がります。クリズムは JAXA が主導して NASA、ESA、国内外の大学、研究機関、企業などと共同開発した衛星です。相模原での運用準備も万全整っています。クリズムには最先端なミッション機器が搭載されています。これらのミッション機器で天体からの X 線を観測して宇宙の構造、進化の謎を解き明かします。これからのクリズムの観測に期待ください。
My name is Lillian Breichenthal, and I'm
リリアン・ライヘンソールです。X 線分光殺傷衛星クリズムの NASA プロジェクトマネージャーです。このミッションで JAXA と緊密に協力できたことを誇りに思うとともに、この度打ち上げを迎えたことに興奮しています。JAXA の首脳陣とともに JAXA、NASA の優秀なエンジニアや科学者たちが一つのチームとして活動することで、難 X 線分光装置リゾルブを作り上げることができました。市場での総合試験を経て、リゾルブの性能も安定し、その機能は素晴らしいことが確認され、衛星試験も完了。チームとしてミッション運用の準備は整っています。衛星打ち上げと待望のクリズムの科学運用の段階を迎えて、 JAXA の同僚の皆様がクリズムの開発試験を通じて数々の難問を乗り越えてきたその努力と不屈の精神に敬服をしているところであります。クリズムは私たちにこれまで以上に詳細な宇宙の情報をもたらしてくれるでしょう。クリズムの挑戦は始まったばかりですが、私たちはその始まりにワクワクするばかりです。
The video was very cool. The first video was a video message from Maejima-san, JAXA project manager. The second message was from Dr. Lichtenthal, a NASA project manager. Maejima-san said that Sagamihara is fully prepared, and he sent a strong message to stay tuned. from audience, we have a question about QUISM. Professor Matsushita, would you like to take this question? NASA's Dr. Regenthal mentioned in her message that QUISM is a mission that has international participation. Yes, that is correct. With the NASA of the United States, we have worked over many years to develop satellites. This time from Europe, ESA is participating, and from not only NASA in the US, we also have participation from Canada. More than 100 scientists are participating in the team, and including engineers. The team is very large. That's fantastic. A very large number of people are involved in this huge mission. Yes. And the second point, maybe Dr. Shidatsu, could you take up this question? In the beginning of the video, there was a test of the satellite. What is the size of the satellite?
The length is 8 meters long and 2.3 tons and 9 meters width, and the solar panel. So 8 meters long. It looks like a microbus size. And with the solar panel, the width is going to be 9 meters. It is extremely huge, right? Thank you very much. And there is another question, Matsushita, Dr. Matsushita. And it is going to be the X-ray spectroscopy mission. And what we will be able to see with the X-ray machine. 1 million degrees in temperature, huge, very high temperature object, 1 million degrees. It looks like relatively low in our own terminology. So if it is going to be tens of billions temperatures, the gravity is going to be extremely important. With heavy gravity, the temperature goes up. And for example, that when it comes into tens of millions of degrees, how the black hole will emit the wind from the core, we will be able to see it. We are really looking forward to that. So tens of millions of degrees and the celestial objects and very high temperature objects will be analyzed. And on top of that, most of the elements in space are not stars. But when it comes into those high temperature, most of them are gas forms. So we will be able to see the essence of the space.
Professor Matsushita, this is a JAXA X-ray Astronomy Observatory, and I believe you have conducted research using X-ray astronomy with the launch of new QUISM satellites. In comparison to the past satellites such as Asuka and Suzaku, Hitomi, and this time QUISM satellite will be launched. With these various satellites, now that we have new satellite, what do you look forward to? I wrote my doctoral thesis with Asuka many years ago. X-ray color and energy can be measured in very precise fashion. That is what is new about QUISM. Light Doppler effect can be used. Several tens of kilometers per second, such velocity can be captured. So I expect that we will be able to take a look at the new world. Thank you. By using X-ray, superhot gas, the velocity of the movement of superhot gas can be captured. Yes, so that is what is fantastic about this new satellite QUISM. What about Dr. Shidatsu? You are a member of the operations team, and what do you expect from QUISM? Yes, I'm a member of the operations team. After the launch, in the initial 3 months, we will be processing data and we will be validating satellite systems. I will be involved in part of that activities. So I will brace myself so that observation will be successful.
So that means for the next 3 months, you are going to be very busy as a team member. At Sagamihara and station and center, you're going to get involved? Yes. Here at Sagamihara, the data is going to be analyzed. So I'm going to move around different places. And at the previous media coverage, the live coverage that you came over to our place, and thank you very much. I hope that we would like to move on to the next stage of this mission. This is about QUISM project. We still have more to talk about. but later on we are going to come back to this topic. But we have to switch the camera to Tanegashima Space Center.
はい、少しお時間あるということですので、
It will be, we have some more time. We have received more questions about CRISM. We would like to address these questions. One of the questions is,
打ち上げ作業関係者に向けて打ち上げ準備状況の報告をいたします。
This is a report of the status of launch preparation from Takesaki Launch Control Center at JAXA Tanegashima Space Center.
H2A ロケット47号機打ち上げ最終実施判断の結果は GO です。
We have just given the final go decision for the launch of the H2A launch vehicle number 47.
現在各系ともロケット打ち上げの最終作業を実施中です。また警戒区域の安全が確認されており、気象条件も打ち上げに支障のないことが確認されました。
All systems are now in final operations. The restricted area has been vacated, and the weather is confirmed to be sufficient for the launch.
従いまして、X 線分光撮像衛星クリズム、小型付き着陸実証機スリムを搭載した H2A ロケット47号機の打ち上げを本日日本時間の午前8時42分11秒に実施します。
Consequently, we proceed with the countdown to the launch of the H2A launch vehicle number 47 with on board CRISM and SLIM, and the launch time is set to be 8:42 and 11 seconds a.m. Japan Standard Time.
機体は最終的な確認作業が続けられており、現在のところすべて順調との報告を受けています。
Our launch site operators have given reports that the final checks are underway, and all operations have proceeded as scheduled so far.
打ち上げ8分前より打ち上げに向けた秒読みが開始されます。
We will start the terminal countdown at T-8 minutes.
480打ち上げ8分前です。現在各系ともロケット打ち上げの最終作業を行っています。また警戒区域の安全は確認されています。
It's 8 minutes to the launch. All systems are now in final operations. The restricted area has been vacated.
460、59、58、57、56、55、54、53、52、51、450。440。430、29、28、 27、26、25、24、23、22、21、420、19、18、17、16、15、
安全系準備完了。
13、12、19、410、409、408、407、406、
車両系準備完了。
404、403、402、401、400。390、380、370、360、
打ち上げ6分前です。現在車上の天候は晴れ、気温摂氏 28.6 度、北の風毎秒 5.5 メートルです。 H2A ロケット47号機の打ち上げに問題はありません。
It's 6 minutes to launch. The current weather at the launch site is fine. Temperature is 28.6 degrees Celsius and wind is 5.5 meters per second from the north. The weather has no constraint for the launch.
本日の打ち上げ予定時刻は日本時間の午前8時42分11秒です。
Today's scheduled liftoff time is 8:42 and 11 seconds a.m. Japan Standard Time.
310、309、308、307、306、305、304、303、
衛星系準備完了。
301、300。
The satellite system is go.
290、89、88、87、86、85、84、83、82、81、280、79、78、77、76、75、74、73、72、71、270、69、68、
自動カウントダウンシーケンス開始。
66、65、64、63、62、
現在ロケットの管制は吉信発射管制塔から行われています。
The H2A launch vehicle is now operated under the command of Yoshinobu Blockhouse.
250、49、48、47、46、45、44、43、42、41、240、39、38、37、36、35、34、33、32、31、230。220、210、200、190、89、88、87、86、85、84、83、82、81、180。
打ち上げ3分前です。
It's 3 minutes to the launch.
全システムの電源が外部から内部に切り替えられました。
170。
The power has been switched to the internal systems.
一段液体水素系準備完了。
The first stage liquid hydrogen system has been pressurized.
150。140、39、38、37、36、35、34、33、32、31、180、 130、29、28、27、26、25、24、23、22、21、120、19、18、17、16、15、14、13、12、11、110、109、108、107、106、105、104、103、102、101、100、99、98、97、96、95、94、93、92、91、90、89、88、87、86、85、84、
2段液体酸素系、液体水素系準備完了。
The second stage liquid oxygen and hydrogen system has been visualized.
74、73、
1段液体水素系準備完了。
69、68、67、66、65、64、63、62、61、60、59、58、57、56、55、
The cooling water system for the flame deflector has been activated.
50、49、48、47、46、45、44、43、42、41、40、39、38、37、36、35、34、33、
ウォーターカーテン散水開始。
31、
The
30、
sound suppression water system has been activated.
27、26、25、24、23、22、21、20、19、18、17、16、15、14、13、12、
フライトモードオン。
10、
The flight mode is on.
同様電池起動。
The thermal batteries have been activated.
全システム準備完了。
All systems are go.
メインエンジンスタート。
The main engine ignition.
12BA 点火。リフト。
Solid boosters ignited.
リフト。プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
60、
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
70、
ロケットは現在東方向の太平洋上へ飛行しています。
The H2A is now flying above the Pacific Ocean to the east.
83、84、85、86、87、88、89、90。
SRBA 燃焼終了。
Solid boosters have burned out.
110、
SRBA 分離。
12、
Solid boosters have been separated.
15、16、17、18、19、120。 110、
小笠原局でのロケット追尾が開始されました。
Ogasawara Station has started tracking the H2A.
第1段エンジンの燃焼は正常、制御系飛行経路も正常、ロケットは順調に飛行を続けています。
The combustion of the first stage engine, true control, and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 48km、148km、秒速約 1.9km です。
Current altitude of the H2A is about 148 km.
上部衛星フェアリング分離。
The upper payload fairing has been jettisoned.
打ち上げ後5分が経過しました。
It's 5 minutes into the flight.
第1段エンジン燃焼停止。
The first stage engine cut off.
第1段、第2段分離。
The first and the second stages have been separated.
第2段エンジン第1回燃焼開始。
The second stage engine ignition for the first time.
「 打ち上げ後9分が経過しました。
It's 9 minutes into the flight.
打ち上げ後10分が経過しました。
It's 10 minutes into the flight.
第2段エンジンの燃焼は正常、制御系飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the second stage engine are true control and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 552km、秒速約 6.0km です。
Calling altitude of the H2A is about 552 km and velocity is about 6.0 km per second.
第2段エンジン第1回燃焼停止。
The second stage engine cut off for the first time.
クリズム分離
Clism separation.
クリズムの軌道への投入を確認しました。
Clism has been inserted into the orbit.
ロケットはこのまま完成飛行を続け、まもなく小笠原局の受信範囲を離れます。
The H2A is in a coastal state now, and shortly it will proceed beyond the tracking area of Ogasawara Station.
次のイベントまで一旦実況放送を中断いたします。打ち上げから約47分後にスリム分離を予定しています。
The separation of Slim will occur in about 47 minutes into the launch. Until the next major event, there will be an intermission.
竹崎総合司令塔からの実況放送は午前9時25分頃に再開を予定しております。
This live coverage will resume at about 9:25 a.m. Japan Standard Time.
We are watching the live coverage of the launch sequence. Crism is separated. We have received a message video, so please take a look at them.
I'm Richard Kelly from NASA's Goddard Space Flight Center, and I am very happy that we are finally on our way into space to begin a new journey with the X-ray imaging spectroscopy mission. I want to congratulate JAXA and the rocket team at Mitsubishi Heavy Industries for getting us this far. This took an enormous amount of work, and my colleagues at NASA are extremely grateful and wish to congratulate them on their success. Astronomers from around the world have eagerly anticipated the launch of CRISM and the new capabilities it will provide for high-resolution spectroscopy and wide-field imaging. We are now a major step closer to exploring the universe in X-ray light with a powerful new tool to reveal what is going on in so many celestial objects in our galaxy and all the way out to distant clusters of galaxies that are emitting X-rays due to their extreme temperatures and energetic conditions. We will soon bring this new observatory online and get to work. So congratulations and go CRISM team.
CRISM project principal
I am Tashio, principal investigator of the CRISM project. Tenma in the 1980s, ASCA in the 1990s, and Astro H in the 2010s. With their then state-of-the-art spectrometers, Japan always led the world in X-ray astronomy. This time again, the world's best spectrometer will be launched into the space. We are determined to use CRISM to capture the world's best spectrums to lead the world in X-ray astronomy. Please continue to support our mission.
The first video was by Dr. Richard Kelly of NASA, and the second was Professor Tashiro, principal investigator. Now we will be discussing CRISM in more detail. From CRISM project scientist Professor Matsushita, and from science operation team Dr. Shidatsu are with us. And about CRISM science research, I would like to ask of them. First, Professor Matsushita. Yes, I was watching anxiously, but successfully CRISM was separated to my great relief. Over the next 3 months, carefully, validation systems will be deployed, and so we will have to continue to be watching carefully. But first step was successfully done. 3 months after, scientific observation will be carried out, and we would like to be able to report the first light. About CRISM satellite, I would like to explain. Can I have a slide? And Dr. Shidatsu, please explain about the CRISM and detector. I would like to explain. Can you see the slide? Is the slide being shared? CRISM length is 8 meters, about 3 stories high, and 2.3 tons is the mass, and width is 9 meters when solar panel is deployed. Height is 550 kilometers, and it's at inclination of 31 degrees, and period is 96 minutes. From the space, X-ray arrives to the left top part of the satellite and will come into the satellite. In this cylinder, there is X-ray telescope. Using X-ray telescope, X-ray will be gathered. The focus of the telescope, the right bottom area, have two detectors. First is X-ray microcalorimeter resolve. Resolve uses freezing systems, including liquid helium, and cooled to negative 273.1 degrees. And at super high resolution, X-ray will be observed. Next is X-ray CCD camera extend. In comparison to resolve, extend has wider angle and will be able to observe an area of a sky equivalent to a full moon at a time. Using these two equipment, observation will be carried out.
So, from my side, the scientific research plan of QRISM. Dr. Shidatsu will give the latter part of the explanation. Then if you go to the website, you can see how to see the cosmic winds. How should I give the explanation on this? This is the topic I would like to talk about. As has been already explained, the telescope and detectors are on board. And what is X-rays? This is the starting point. X-rays are part of the electronic magnetic waves, like the ultraviolet as well as the lights. They are part of the electromagnetic waves with the high energy, with the short waves. X-rays cannot penetrate the atmosphere, and so the satellite is essential for the observation. As has been already explained, 1 million degrees and the 100 million degrees, the objects will be able to be observed by this X-ray astronomy. There are two detectors on board. The first one is resolved. This means the resolution and also determination. So these two things are contained in this term. Now let us compare the performance. As you can see, this is about the Astro H observation results. Perceives the clusters of a galaxy, X-ray spectroscopy, and you can see the colors in the X and Y axis. You can see those are the two detectors that are going to onboard and similar to the ones that we have. The black represents the Astro H microcalorimeter, and the red one is a Suzaku CCD. The microcalorimeter, if it is going to be used, X-ray color, that is the axis, you will be able to see how accurate it is. And similar to the sound, when it comes to the light, it is affected by the Doppler effect. If it is approaching, and then the blue shift, and then if it is going distant, red shift. And this is going to be applied to the observation. X-ray color can be observed accurately, and you will be able to see the sources, or like the high temperature gas, and can be analyzed accurately. And on top of that, you can see chromium and manganese. Those rare elements, they are going to be X-rays emissions, as you can see in the chart. Those small, the minor, the X-rays can be detected for observation. And then X-ray space-based space. How is it going to be observed? When it comes to the Milky Way, you can see the near-infrared observation on the top. You can see the disk that spreads around. We are within this disk. And then X-ray has observed this galaxy on the bottom. In the bottom, you can see a different view. X-rays will use the emitted by the gases with high temperatures. In the case of the Milky Galaxy, you can see millions of degrees of X-rays can be observed. You can see the speed of the cosmic wind, and there are different the celestial objects. They are called supernova remnants. Those are two remnants. The left one is about 300 years ago. It is the remnant of the supernova explosion, and it's 16 light years wide. And on the right-hand side, 11,000 years ago, there was the explosion. and 250 light years expanse. So you can see the effect of the explosion. XRISM will be able to observe X-rays emitted from those supernovas, and then we will be able to observe the elements and the speed of the gases. In fact, around ourselves, when it comes into those elements, they are produced in the supernovas. And as you can see, we will be able to analyze the alchemy of the space and the speed of the wind and the evolution of the galaxies. We will be able to detect them. And you can see this round object. These are the clusters of galaxies. Hundreds of galaxies are going to be combined together. And you can see this is the enlarged picture, X-ray picture, which is enlarged, and about 600 billion years away, with the expanse of several light years. And they are trapped in the high temperature gas in the core. And most of the elements in the space are produced and then exist in the form of a high temperature gas. XRISM will be able to detect these objects, and then how those objects are growing in the space-time. They will be able to be observed. And there's some percentage of the elements that were produced in supernova are spreading around, and we will be able to observe them. In the core of this stellar object, this is M87. And this M87, this X-ray picture can be captured on the left-hand side. From the galaxy, there is a high temperature gas is emitting. And on the right-hand side, this is the microcalorimeter, which captures the spectra, which is expected to be captured. The pinkish, the dotted line, represents the Suzaku results. And you can see different kinds of information, the data can be captured. A XRISM, a satellite, will be able to observe the emissions of those gases from M87. Then, how's the wind blows from this place?
Yes, thank you. Shiratsu speaking. M87 was just mentioned. In the center of the image of the galaxy, in a white square, that is the center of the galaxy. In X-ray, we can see that it is very bright. And if this is enlarged further, it is about 6.5 billion solar mass. There is a supermassive black hole. It is known to exist. And such supermassive black hole is estimated to be at the center of each galaxy. Other than supermassive black holes in the universe, there are various black holes, including small and large ones. For example, at the right side, this is a different galaxy, and visible light and X-ray are superimposed. And looking at this, other than at the center of the galaxy, there are some bright spots under X-ray. And this is also a black hole, and these are paired black holes. And these are several tens of times larger than solar mass, stellar mass black hole. And these are circling each other in a very short distance. They are attracted by the strong gravity of the black hole, and they are falling into black hole as they encircle, creating a disk at the center. And the gas temperature is as high as 10 million degrees, emitting very strong X-ray, and that X-ray is observable in the image above. There are small and large black holes. They not only absorb things, but as Professor Matsushita mentioned earlier, high-speed gas is emitted. For example, on the left side, this is a jet, and light velocity is 300,000 kilometers per second. The speed is as fast as that, and the falling disk above that, there is a wind emitted, as shown on the right side. the velocity of the wind is several hundreds of kilometers to 10,000 kilometers per second. Earlier, rocket, when Chrism was separated, it was traveling at about 8 kilometers per second. In comparison, the speed is much, much faster. And in a supermassive black hole, these jet or wind are emitted, and surrounding stars and gas may be moved and affect the formation of the galaxy itself. That is the estimate. But why do jet and wind come from the black holes? And to what extent do they affect the surrounding environment? That is not fully elucidated. With a Chrism, we hope to be able to understand this mechanism. For example, as shown at left below, around the black hole, there is a wind. And let's say we observe this wind. Near the black hole, there are various types of X-rays with different levels of energy. And X-ray, the gas coming out, if we observe the wind, we can look at the element such as iron that will be absorbing a certain level of energy. And as shown on the right side, we can see a spectrum of absorbed energy. The wind is moving, and due to Doppler effect, from the original energy level, absorbed energy is observed at a little different time difference. And with that, we hope to be able to estimate the level of energy. And the black line showing absorbed energy, we were able to have very rough idea, but with the resolve on Chrism, each line of absorbed energy can be understood more precisely to understand the intensity and absorption of energy, how much gas at what velocity are emitted to the surrounding environment, and how much it is affecting the environment. We hope to understand that better. And with X-ray observation, time-space distortion may be understood. That is also hoped. Near the black hole, because of theory of relativity of Einstein, there is a distortion of time-space, and EM wave that is emitted will be observed with a distortion. The right side diagram shows the iron light line emitted from the black hole, and there are several peaks spread over widely. And this spread shows the distortion of the timeline. By understanding the shape of the emission line, we should be able to understand the degree of distortion of time-space around black hole. And black hole rotation, the faster the rotation, the effect is larger, and the range will be spread wider. So by understanding this, we should be able to measure the speed of the rotation of the black hole. Not only near the black hole, but at a distance from black hole, there will be a gas and wind that are absorbed. Then smaller emission lines and absorption lines will be mixed. With the existing equipment, it was difficult to distinguish, but with resolve, as shown in red line, various different components can be separated to understand the distortion of time-space around the black hole in more precise way. That is the hope, and in this way, so this is only a part of what we are hoping to achieve with a Chrism. We would like to understand the mystery, unravel the mystery of universe using Chrism.
Thank you very much, and having listened to your presentations, Chrism has a very fancy name given to. The resolve means the dissolution, and then resolve also means determination and fortitude, and then extend. This represents extension of the idea, so to speak. Similar to Chrism, well, as captured in Chrism, how do you come up with a specific naming? Microcalorimeter, Rich Kelly, Mr. Calorimeter, AK, who has named this machine with the instrument in that way. Thank you very much. And the viewers probably are most interested in this topic, the distortion of space-time and black holes. And it is going to go up into 10 million degrees and I am a scientist on the solar system, and then the temperature is like 1 million degrees, but it goes up into 10 million degrees. The flare is supposed to be the reason for this kind of creation. But in terms of the theory, do you have any specific ideas when it comes to the black hole, the temperature surrounding it? The gas comes down, declines, and it resolves and rotates at a huge speed. And then, as a result, the temperature goes up to 10 million degrees. So there is this theory, but theory is going to be corroborated and by the specific observations and by the result or the chrism. And that's the process and that the scientific mission is going to be made as for chrism. Thank you very much and for your talk. Next, Slim.
I would like to introduce Slim to you, and we have a video message from the project manager. So please take a look together with the video introduction of the project. Hello to everyone watching this live streaming event. I am Shinichiro Sakai, project manager of SLIM, Small Lander for Investigating Moon. I think you're all watching the live streaming with much excitement, waiting for the launch of SLIM. I feel the same. It has been 7 years since the start of the project. If you go back to when the idea was originally conceived, it has been more than 20 years. With the support of many and efforts of all those involved, we are now welcoming the day of the launch. We have dedicated so much efforts and great deal of thinking in SLIM, with which we aim to achieve lunar landing with unprecedented precision, to open the door to the next generation of lunar exploration. We are determined to stay focused even after the launch. From the era of landing where we can to landing where we want. Please continue to support us.
はい、こちらも酒井プロマネから大変力強い言葉がありました。スタジオにはスリムプロジェクトメンバーの森先生とペイロードマネージャーの大竹先生にお越しいただいています。打ち上げ続いているところですけれどもいかがでしょうか。
はい、先ほどですね、酒井プロジェクトマネージャーの最後のコメントのところに降りやすいところに降りるから降りたいところに降りる探査へというそういう